that will be even as well. So we have this is what we have now. Now let's plug in. So this is the case now, and let's look at this x here. And now this guy is G prime, and we have these critical values here. Negative 5, negative 6, negative 5, 0, 2, 7, and then there's no other coefficients here. So what happens to the sign of G prime when x is bigger than 7? So that will be a plus. And when this is even, we cross over the critical value of even power, even multiplicity, then that means the sign does not change. So from here to here, when this guy's even, then what happens here? The sign does not change. And now you're crossing of even power, the sign does not change. When you cross over odd power, the sign does change. And then when you cross over here, then the sign does change again. Let me see. Yeah, sign does change. And then when you cross over even power, then the sign does not change. So what we get is we get the plus plus, the minus plus plus plus. And so what that means is the G prime is plus. That means this is actually going up. And then this is going up. And then going down. And then going down. And then what is plus? That means this is going up. This is going up. And then this is what? Going up. And then going up. So if I look at this here, what do we see? We see that at negative 5, we will reach maximum. And then when you go down and go up, then this will be the minimum. Yeah, this minimum right here should be written right here at 0. Something of this type, this should be minimum here. And then it goes up, and then goes up. So we only have maximum and minimum right here. So when you have these kind of factor form of a polynomial, a factor form of expression, then what do you do? Then all you have to do is look at these exponents here, the multiplicity of each zeros, and then figure out whether they're even or odd. If you tend to be even or odd, when you cross over that critical value, then you change the sign. Any questions here? If you have no questions, then I guess I don't have to explain too much here. Okay? I'm going to clear this. And the same thing for number 4 as well. Okay, now let's see number 5. Yeah, number 5, most of you number 5, most of you got it right. Now here, let me make some comments about this. If you have number 5 here, now this is general solution. There's a W in here. But now here, let me make some comments on this one too. This one, okay, look at this. So D is equal to this. All of you will get something of this sort. This is D. Now there are a few cases where there are a few solutions out there. Some of you, instead of trying to minimize D, you minimize D squared. So you try to find the minimum of D squared, which is okay. So if you minimize D squared, so find what? So find min D. So this is not fine. Oops, fine. But how about fine? How about let's say K, and then equal to D squared. You do this, and then you say what? Find min K. Then what? Find? Oh yeah, min D squared. So let me put D here. So it's min. So find K. Find K is equal to this, and then find what? Sorry. Let me do this here. Let K be this. So let K is equal to this. And then you could have said the find min K. Find min K. This is small, big K. This is big K. And that's okay. Because D is a constant quantity, so even this is min K with this, and then you try to find min K, that's okay. Now, either way, now let's do this. And then now you have to substitution Y plus K. I think most of you, what you did was you replaced this one right here by x squared. But actually, the much better way is do not replace y by x squared, but replace this y squared right here by y. Sorry, replace x squared by y. If you replace x squared by y, then it's going to be so much easier. Okay, you know what I'm saying here? Replace easier if you replace x squared y instead of the other way. And so you would get the distance in terms of y. If you replace x squared by y, it is going to be so much easier. That's so much easier to do it that way. Alright, anyway, that's that. So let me just erase this. Any questions here? Now, the biggest problem is number 7. Number 7, I don't think anybody got a perfect score on number 7.
Works so hard on the thing.
Okay.
Right?
Last night, yeah.
Huh?
What was wrong?
I clicked the wrong button.
Not many of you got this number 7 right. I don't know whether there's any one person right. Yeah, I don't think anybody got the perfect score on number 7. Okay. And number 7, this is what I recommend here. The solution is actually quite short. Of course, you have to know what to do. Now, this is the way I do it. I do it by completing square. The better method is what? The better method is by completing square. So let me write this down. Better method is what? Better way. The better method is better method by completing square. Most of you did it by what? Most of you did it by what? Most of you, this problem, it's solved by what? It's solved by what? So, did it by
Discriminant
calculus. Now the difference is whether you're using the discriminant or by completing square, you are exactly doing the same thing. But the only problem is, if you solve the problem by discriminant, you're not exactly sure what's going on. You cannot really see what's going on. But you know what? Because the discriminant looks much easier, and so also if you do this by discriminant, you have to assume a lot of things. You have to already know all the rules behind. It's a very heavy theory base, and because of that, most of you. When those of you who use the discriminant, they don't know what was exactly going on. So you have an idea, and again, for the reader, you cannot really understand what your solution is. If you present the solution by discriminant. Okay, I'm not, so discriminant is a good thing. Of course, I know what the discriminant is. I know the quadratic formula. And by the way, as a math teacher, when I deal with quadratic equations and quadratic functions, do I use the quadratic formula or do I use the discriminant? And I don't know whether you know, but I rarely do. I don't use the discriminant. I don't use the quadratic formula. Why? Because it's too much heavy theory. All your theory must be memorized.
So you thought it was submitted or it was never submitted?
I thought I clicked submit, and then
it is doing the same thing, but it is
the page I was expecting it to say like confirmed you submitted, and instead it just showed me there.
These are the two methods here, but the two methods are here. But
I don't know. I think
the completing square, this is actually by far the superior method. So let me tell you this. So these are not just two different methods. They're not just two different methods, but let me tell you, the method by using the completing square is the superior method. I will rarely say this. It is the superior method. Because you know exactly what is going on. You know exactly going on.
Maybe you could talk to someone on the phone.
You're kind of stepped away from what is exactly happening, and you don't understand what's really going on. And for that reason, many of you did
So you're
make
just
some
going to
mistakes.
take that?
Yeah. And
I don't know what to do. She just said no.
Or your argument is incomplete, or something went wrong there. Okay. So let's look at this. So this
Well, that's a
solution.
little ridiculous.
I don't think anybody did it this way. Almost all of you did it by discriminant. And by the way, I'm going over that here.
What does the website look like that caused me to
something on quadratic functions and quadratic equations,
It's like it
and you will have to.
has a button here that says save
and something similar will happen.
save
Okay, so now
and
let's look at this.
continue.
Number
And then
7.
it says save
So
and
number 7,
exit.
fx equals this guy. There's a p in there, and V1
And they're the same
exactly
color.
V1
So
exactly
that's
one
gonna seem like it's your fault.
one inflection point.
This machine.
Okay, so the game
I
is
should have
this.
had enough
The
time to
goal is
log back in
here's
after
point
doing
one
that and
exactly one inflection point right
repaste
here.
it.
Okay,
And
so
then
we
what
take
you
the
worked it
derivative.
to the
Okay,
very
so you
last
get
second?
fine, and then we get that, and that's no
No, I mean,
and so
I
almost nobody made a
had like
mistake
a
here.
couple
Everybody
minutes,
got
but
this,
it's
this
like
right here.
I didn't know what happened. I was
You
like,
got this.
what
Well, that's
happened?
good.
I was like trying to figure out what
Oh.
And
happened.
then what we did was we just said,
And
we
my
need to factor
browser
the text
needed to
all
be
time,
updated,
factor
and
it,
it was
and then this is what we
buttons
get.
weren't
And in
clicking,
this
and
case,
so I had
because
to
we have
sign
X
in
squared
through
here,
another
because I'm
browser.
ready to do this by 2 squared, what I did was I force factor, in this case,
It's
the
my
TX.
fault.
Well, I don't. If
So
it's
note
so
that when
important
I
to you
factor
and you
6
wait
here,
for a
you
year,
notice
why
that
would
that
you
side
working it to
becomes
the
0
last possible moment to
becomes a
submit it?
fraction. But the reason why I factor
Just doesn't
the
matter.
16x is
I
because
had
the
a
leading term
test.
right here becomes
Yeah,
x
but
squared. And then after we get
I
to
know, I
x
just
squared
wish
here,
I was
just play
dead.
with
I
it.
want to die. And I have work in my
we
ears.
factor something
And
so
I
that
feel like I'm a
inside the
fraud.
parentheses we get
So
x squared.
I
Not
don't want to get up.
so that the coefficient in front of the
So
x squared
unhappy.
is
I
1.
don't want to be
And then
stuck
once we
here
have that, we
somewhere.
will know
I
what
was
kind of
just
zeros we
want to
have
go
here.
somewhere.
And here, many of you, all of you,
I'm stuck here again.
And so once
Such
again,
a
when you do
fucking
this
idiot.
discriminant, some things are hidden. You don't exactly know what you're getting into. And it's hard to understand because the discriminant is like a nice tool, but it is a step away, removed from the actual problem. So now what I do from here is we now put the square. And because we have this x squared minus 4x, it is very good, easy to complete the square. You add a 4 here and then negative 4 here. And then the first 3 terms here, you get a complete square. And so now the final form is this right here. This is what we get. This part right here is now the completed square form. And note that this is x to 1.
I mean,
So it
sure, you
looks
could
like we
call
have
them
an
or go to
inflection
them in
point right
person
here.
and explain
And because
it.
it's off power, we have an
I
inflection
did. That was your response.
Okay, so now if you look at now what we want to do
Okay,
is now
so
our
if
focus
it's
is
that
this
important
part.
to you and you're just gonna be
Our
like,
focus
I got
is this
rain
part.
power.
I don't understand how that's acceptable. You did the application, you hit the wrong button, and it's a confusing interface.
Now this guy is x minus 2 squared and the plus negative 4 plus c over 10. So the question is whether we will be able to factor this or not. The question is whether we will have whether we will have zeros or not. If this can be factored as 2 linear factors, then
Where
of
is
course
this-
we
where are
will
they
have
located?
we will have 2 more factors. So the question is, will
Brown.
this become this? Will this become 0 and this something, and then times something? That is, will this be something x minus r1? We may call this. Will this be x minus r1 times x minus r2 like this, where r is a real number? Or will this be x minus maybe r squared? Will this be able to factor this way? And then square here. We have a double here. And then, of course, the third case is not factorable. Not factorable. Not factorable over real. So let me write this down. So not factorable over real. So let me write
sounds
this
like
down.
it's
So we have 3
designed
choices.
poorly and
This is not
wanted to see
factorable
this thing. I know they don't care.
over real.
Which they
That is, we have no real zeros. That is no real zeros in this case. No real zeros. No real zeros. No, okay? So basically, 3 factors. Now let's see what happens here. So first of all, the first case is this. To have exactly one IC, well, let's see. What happens if, let's say, maybe I can take this out. How about this? This guy right here. This here. So you know what? Let me just erase this part right here. I think this part, I don't have to put it there. We will know when we get one IP, one instruction point, but we don't know what it is.
I just don't understand if they were like so excited.
Okay, so first,
I
had problems.
C over 10 is
I
actually
had
bigger
things
than
I
zero.
couldn't. I was trying to finish it. I told you last night I was trying to
So
finish
C over 10
it.
is bigger than zero.
Night before last I was
This
trying to
kind of
finish it.
idea is bigger than zero. And if this guy is bigger than 0,
Fuck.
then it will be
I
this
should
case
have
right
worked
here.
on that fucking
So,
resume
if
like
it's
an
this,
idiot.
the
I
first case,
shouldn't have.
if it's this case, if it's this case right
Should
here,
have just didn't
then
work
this is
on it.
actually this case right here. This will
Why
be
did it
able
do
to
that?
go
Oh my
this
god.
way, not factor over real. That will refer to that case. And in that case, we cannot factor into two linear factors like this. We allow only real numbers only. And therefore, if that is positive, then this is not factorable. And then that means we have a square here, but plus something positive. So this guy will always be positive. Again, this guy right here, in this case, this guy will always be positive or direct. Not factorable, no 0 there. And so now we only have a inflection point generated from this x right here. X the first power. So therefore we have exactly one inflection. That's the case. So everybody, do you follow me here? It is much easier to see than the discriminant. You're actually dealing with the quadratic expression right here. When you have x minus when you have x minus 2, and then minus 2, and then square, and then let's say, for example, square, and then let's say how about let's say plus, and then 7, for example. So this, let's say this guy is 7, so we get this. Now we can see that this guy right here is always positive. And if this is always positive, that means there's no real 0. That means you only have one inflection point. The inflection point occurs at x equals 0. This case. That's it. So now the question is, what happens when this guy's actually when this case right here? So what happens if this guy's actually 0? What is this? If negative 4 plus 0
when my alarm goes off, can you not turn it off for me?
In this case, what exactly happens?
Which one?
What happened
I mean, which one?
By the way,
The
My
music.
alarm.
you did not separate this case.
Yeah, you did.
This is the case when the discriminant is
the
actually
alarm
equal to 0. But again, when you
It was
use the
ringing,
discriminant, you're a
and
little
then
bit
it said,
away. You're a
"Hey,
step
Siri,
away
stop,"
from the
and
actual
I didn't
problem.
get up.
You don't know exactly what
No,
you're
that's
getting
not what
into.
happened.
You don't have on the.
Your
So
phone.
how did
Your
my
alarm
alarm
didn't go
stop?
off. Your alarm
If
didn't
this
go off.
is
That's
the
not true. I heard it. I was listening to it, and then I kept laying in bed.
This guy right here. This guy right here.
Where's your phone?
60x times x minus 2 squared, and this guy will be 0. Right there.
Where?
It's
So
right there.
I
x
didn't-
equals 1, we have the inflection point x equals 0. But how about x
I
equals
don't
2?
think so.
Notice that it says double.
I remember turning the music off, but I
It
didn't
says
turn the
double
alarm
root, and so the sign does not change around the 2. In this case, therefore, no inflection point. So let me write this down. In this case right here, in this case, no inflection point at x equals 2. Again, no inflection point at x equals 2. Even though at x equals 2, the second derivative is 0, but it's a double root. It's a double root, and therefore we do not get an inflection point. The sign around plus before and after 2 does not change. So no inflection point. No inflection point, so we only get exactly one inflection point. So if now minus 4 plus 0 can equal 0, then what we get is we actually get exactly what? Basically we get what we get this point right here. We get exactly one inflection point. Again, if this is 0, it's easy to see. That means you get a 0 here, and then you can see the f prime value is right there. And so, so you get this, x equals to the double root, and so you only get one example, one inflection point. And now the third case is this. The third case is, as most of you figured out, is the case when this guy right here is actually less than 0. So what happens if this guy right here is less than 0? So now let me, I think we need to see better, so let me erase this stuff here. So again, if this minus c plus c of 10, minus 4 plus c of 10 is less than 0, so let's look at this one more time.
What happened?
Okay, I'm sorry. I need to write her.
Then that means this becomes a negative number. And if this becomes a negative number, then we get something squared, and then minus a number, and the minus something positive, and so we now get this guy right here. We get into this case right here. So if minus 4 plus 0 of 10 is less than 0, this is actually a case when the discriminant is positive. You get this. That means f double prime, that means f double prime is actually going to be this. So in this case now the question is, how many inflection points do we have? Then we have x to the first power here, and then we have x minus r to the first power here, and x minus r to the first power here. So when this guy is less than 0, how many inflection points do we get? Can you tell me? If that minus c plus c over 10 is less than 0, how many inflection points do we get? We get 3 inflection points. Does everybody get this? If that minus 4 plus c over 10 is less than 0, we get 3 inflection points. Because you have this one is 0, and then R1 and R2. Because there's something scored minus a number, minus 7 or something, then we can factor this. So we get 2 zeros here. So we get 1, 2, 3, we get 3 inflection points. So, however, except, this is how there's exception. So what happens if this parenthesis right here has a root or a 0 at x equals 0? Now we already have a 0 right here. Is it possible that this guy has the root 0? And yes, it's actually possible. So when you plug in x equals 0 here, when you plug in x equals 0, you know what we get? So how is it possible that we get the whole thing 0 by plugging in x equals 0? And if we do that, then we will find that c must be 0 in that case. I don't know, do you follow me here? So the parenthesis has a 0 at x equals 0. So when is the whole thing 0 when x equals 0? So the whole thing is 0 when x equals 0. That's what happens when t is equal to 0. So this is 0 when the root is x equals 0, and that happens when c equals 0. So in this case, what happens is we will also get a factor of x here, and so now let's see what happens. So if c equals 0, let's see what happens. So we can actually get this guy. Don't guess too many things. If c equals 0, let's see what we get. If c equals 0, then f double prime is this, and then the c is 0. So now this c is 0 here. This c becomes 0. And so we get this. And then we get this guy right here. So now the interesting thing happens here. When c is equal to 0, then x equals 0 is not an inflection point anymore. No inflection point at x equals 0. Why? Because x equals 0 is now a double root. So before and after x squared, before and after x equals 0, the sign does not change. And so what happens is in this case, we get exactly one inflection point at x equals 4. So the final answer, what is the final answer? Final answer is right here. Final answer, when this case right here, we get one inflection point. And then on this case, we get one inflection point. And then on this case, we get one inflection point. The parts which I marked in bold, they are the cases when we actually get one inflection point. And so in this case, when you solve this guy right here, it's not out to C, we get C is actually what? C is bigger than 40. Then what is this case right here? This case, that's when C is equal to 40. And then the last case, the most obscure case, when C is equal to 0, we get exactly what? We get exactly one inflection point. So now we combine all of these things here. And so exactly one inflection point when c is greater or equal to 0 or x equals 0. So it's not easy. Okay. I think number 7 was probably the most difficult to solve theoretically. Okay, but anyway, so that is number 7. It was a little bit tricky, right? Yes. I think most of you.
Could doing it by the discriminant get you those answers, or will it only get you c is greater than 40?
Right, no, when the discriminant becomes 0, that means you get a double root. And if you do get a double root, then you don't get an inflection point either.
I see, okay.
Now, the only problem is this. When you use discriminant, it looks easier. But a lot of the things are hidden. It's behind, it's like something works in the backstage. And you cannot really see what's happening in the front stage. You know what I'm saying here? Okay, if you use discriminant, also you have to know so many formulas. Now, if you follow the way I did right here, which is a completed square, then you don't have to know anything about the discriminant. And you don't have to memorize the solution. If you have this, then you have two solutions. If you have this, then double it. If you have this, then you have no solution, no real solution, opposite solution. You don't have to memorize any of that. So, it is more work. So when there's two methods, working like complete square versus discriminant, let me tell you, practice all of you use discriminant. Because this guy, you know, easy, all you have to do is one formula, right? But when you're using discriminant, there's so many things that you are working the backstage, you don't exactly know what is exactly happening in the front stage. You don't know. Something is hidden. And then you have to memorize all the rules. When D is negative, then you have this, and when the D is positive, you have this. Here, when you work with complete square, then you don't have to memorize any of that because it is clear from the problem itself. And I probably will be testing you more on this year. I know when you were taking intermediate algebra or pre-calculus, somehow the discriminant became a very popular solution among students because it is kind of neat. And but again, a lot of students don't know what is happening here. So they like the discriminant, but you are not ready to fully analyze with the discriminant. So this method here, personally speaking, this method here, I do not recommend. So I rarely tell you which one is the superior method, but in this case, this guy is the superior method by complete square. Okay? So if you just do the complete square, you know exactly what is happening in the front stage. There is no guessing. If you have x minus 2 squared and then a negative number here, then you know that that means this can be negative. For example, if this is a negative number like this, then that means you can factor this. Why? Because you have a squared minus b squared. You can actually factor this, and when that is less than 0, when this is less than this case right here, when this is less than 0, we know that it's going to look like this. That's not how you see it. That means you get two real roots. Why is that? Because something square minus something like minus 7, then you can do this, and then minus square of 7, that's plus square of 7. You know immediately that you can get this. And if you get this, then we get 3 inflection points. There's not much to memorize. Not much to memorize here. You kind of know. Because you have to also know this guy here. So you have to understand that. So this one, the top way method, the square, this is understanding based. This is understanding based, whereas the discriminant here, this is memory based. Again, the discriminant is the memory based. You have to know so much already because what you see doesn't tell you what's really happening. So behind at the backstage, you have to know all the formulas and all the patterns. It should be there. When the discriminant is less than 0, this happens. When this is positive, then this happens. When the discriminant is 0, then this happens. Unfortunately, most of you did not get the case when the discriminant is 0. That's the case when people say, you missed this guy. And yeah, that was a few points as well. Okay? Everything, and if you miss this guy here, this is a big one here. Because we have to know it could double up. We have a 0 with this guy's x here. What happens if this guy also creates the x as a factor, and that's positive. And that's what happens when t is equal to 0. So as you see, when you look at c here, this guy actually produces x equals 0. And then now x becomes doubled up, and now normal inflection point x equals 0, so now we get this right here. Alright, I think that's good enough here. Okay, so I'm not going to save this, there's nothing much here. So I'm just going to clear all the drawings here. Alright? Okay, so that's it. Again, for those of you who have sent me some files by Canvas mail, I didn't have a time to go over those yet. I found about 5 emails, so I don't know whether all of you made a comment on that. But anyway, Just give me one more day. I might have to make an adjustment. I will make an adjustment to your score if I feel that you need more credit. Okay? So I will go through the email. So any solution sent by hand of mail, I will look it up hopefully today. All right? Okay, so now let's now move on. Let's now, we have to move on here. Don't have too much time. So what I'll do is I'm now going to, let's now continue. Section 4.1.
Okay, Professor, before you do 4.1, may I ask you a question about this exam?
Oh, what about this exam? You mean
that
was a math question here?
Oh, not a math question, but I guess like I got my score back, but it didn't change my grade because it's listed as an imported assignment. So would you be able to change it so it's under like exams?
Is the classified as an assignment?
I think a lot of people, I don't know if it's just me, but mine's listed as an imported assignment, so it didn't.
I made that mistake sometimes. So what I'll do is, after the class is over, I'm going to check, and if it's categorized separately, then of course, under the score, it will be different, right? So yeah, so I'll change that. Okay, so I'll check this. So once in a while, I'll make that mistake here. So this is something easily fixable. So after the class is over, I'll check that midterm 3 is classified under the midterm rather than homework or something or assignment or something. Okay, I'll check that.
Okay.
So
thank you. I appreciate it.
You'll be able to fix that immediately after, like, hopefully, like within 30 minutes after the class over. I will try to fix that. Okay. I'll fix that. Okay.
Thank you.
That, okay? I'll do that. Well, by the way, you know what? Let me see. Maybe it's a good time for me to go through the decimals here. Let me go through the graphic calculator. And now, here, what I would like to do is I would like to make some comments about the problem we had on today's step as well as any problem. So now here, let's talk about this. Here, what I'm going to do is let me share this. Am I sharing this page? Oh yeah, I'm sharing this decimals, right? So what I want to do is, how about this? Here is fx equals x squared. Yeah, this red curve is fx equals x squared. Now, do you remember this from here? This from right here? Okay, so here, let me magnify this a little bit. So we have this from right here. Now, this is, on our example and on our test, we had a problem. So we had a problem. This curve, by the way, is y equals x squared. This red curve is y equals x squared. And here I've already drawn this, typed it in, and so we can see the black line. The black line is the tangent line, and the red and the purple line is the normal line. Now what I'd like to do is, does this have anything to do with the problem which we studied in optimization? And yes, it is. This does have something to do with optimization. And actually, this suggests that there's actually a different way. The problem we had was this: on a parabola, given a point, what is the point on the parabola which is closest to that given point? And when you look at the exercise, we had a point. We had a problem. One problem we had was we have y equals x squared, and the point is right here. The point is 3, 0. And what is the point on the curve y equals x squared, which is close to this point? So now, if I move this, let's say, how about this? Maybe I'll mark it right here. How about if I mark a point, maybe or at 2 right here? Let me mark a point at 2 right here. So we have 2 points. So this one here, let me mark this as round point. You know what? Let's mark this as purple point. Okay, let me make it purple. Okay, purple right here. So the question is, let's say, what is the point on the curve y equals x squared, which is closest, the point on the curve y equals x squared, which is closest to the red point? So this one here, the way we saw was through optimization, right? But now this time what I'm going to do is this. How about this? Let me move this tangent line and normal line around. And then, let's look for a line. Let's look for a normal line which is passing through that red point. And let's say at 3, 0. Right there. 3, 0 right there. So right, now if you look at that one right there, now I drew the line. Now if you look at that line there, what is it? The tangent line is the normal line. And you said 3, 0. now part of the normal line. And so when you have a normal line passing through a point, you know what that means? What that means is the point on the curve y equals x squared, which is closer to the point 3 comma 0, is actually a tangent point right there. So the tangent point is 1 comma 1 right now, if you look at the diagram. But this is of course all an estimate. It's not exact. The graph is never exact. So we can see that right there, if this is what we all see, that is the point closest to that point 3 comma 0. So if that is what I'm saying. If you find the point P on the curve which is close to point 3 comma 0, then what that means is that then the point 3 comma 0 happens to be a point on the normal line. So what that means is here with point 3 comma 0. So what is the point here? The point here in this case would be this. In this case, what I'm saying is, so now what I'm saying is, so this point right here, that is the, let me write this in red. So now what I'm trying to say is this is the red. This is now the closest point. Is that the closest point? Yes, that is the closest point. Now that is the closest point. And if that is the closest point, then what happens is this point right here, this point is on the normal line. This point is on the normal line. Then this point is on the normal line at the closest point. We have this right here. So this is the pattern we see. So now what happens if you now let's say have a point like 2, 0, 2. So on the test you just took, the point was given on the y-axis, right? Everybody had a point on the y-axis. Now this time, let's see what we can do. So what I'm going to do is I'm now going to move this tangent line around and the normal line, and then basically I'll move it here, and then here at least graphically speaking, or now this is the point right here. And so if you now find the normal line which passes that point 0, 2, then this is now going to be the closest point. So this is now the closest point right here. So the question I gave you, finding the closest point. Finding the closest point has two ways. So given a point, now basically what I'm trying to say is this: given a point, given a curve, and a point not on the curve. How do you find the what? Well, how do you find the closest point? Find the closest point. Find the closest point on the curve. Find the point on the curve. How about, let me write like this. Find the point on the curve. Find the point on the curve. Find the point on the curve closest to the given point. Given point is not on the curve, of course. This is not on the curve. Okay, so this is not on the curve. In this case, the two methods. What? One by optimization. That's what we studied, in this chapter. And second one is by what? By normal line.
Anyway, I need to dinner.
So, if you know how to do the method by normal line, then you know what, you can get it too. Okay? The normal line, right there. Of course, the trick is that the normal line method, you have to be a little bit careful because there might be another one right here. Let me see this one here. Another method, if I bring this over here, and then you might actually get this. Look at this here, and then pass through this one right here. And then if I go to the origin, it passes through that one as well. See the origin at the origin, the passage of this point. Now at this point here, what you will realize is that this point at the origin, this distance is actually a relative maximum. Because from up to here, the distance is actually what? Getting farther and farther, farther and farther. And at this point here, the distance reaches maximum, relative maximum. This is not the absolute maximum. That is, the distance is not an absolute maximum, it's the relative maximum. And then from here, now they get closer and closer again. And then as closer and closer again, and now what happens? Now this point right here, when it reaches back to the minimum again. And then after that, it becomes farther and farther. The distance becomes farther and farther. Get that? Anyway, if you did understand that, then you can make use of it. So anyway, the normal line I just introduced in this class, but you know what? The normal line has actually many uses. That includes the maximum, minimum, and when it comes to optimization, normal line comes into play as well. So this is a completely different method. So if you can find the normal line to any curve here, which passes through that point right there, then at that point you that's a critical point, and you can check it. Whether you get a max or min or something, it could either be max or it could be min, or it could be neither one, but it will be a critical point. Okay, so far so good. Okay, so now let me erase everything. I have spent a lot of time here. Okay, so now let me erase everything here, and now let's go back to our notes. No, cancel. Let me go back to our notes. Okay, am I sharing the screen here? I'm sharing the screen. Now let me open up section 4.1. No, section 4.1. Where is it? Okay, so section 4.1 is 4.1 right here. Yes, let's go back to section 4.1. By the way, I am planning to give you maybe some more quizzes, although I don't know when. It could be tomorrow. Okay, so be ready. You only have about a week more to go now. Okay, so section 4.1, we did example 1, and by the way, I did we have all this. We have all this. We have all this. Okay, you know what? Let me open up the file with the answer. Okay, let me just, you know what, since I don't have too much time, I did prepare it, so now let me write all the let me use the file which have all the answers. Again, when you study on your own, then I do recommend you to study the page with no answers and with no notes. You should be able to do the prep on your own, okay? And then after you spend at least maybe 5 to 10 minutes on each problem, then you look it up. And yes, I did make the correction here yesterday on example 2. There's some mistakes, right? And so what I did was I did make a correction. So now, hopefully, if any of you find mistakes, then please let me know. And especially the solution file, I was writing all these solutions here. Yeah, so I'm bound to make mistakes. So if you do find any mistakes, then please let me know. Again, example 2 is corrected. Okay, example 2, we did that last time, and so now let me scroll this down, and then we did all that, and the basic sigma formula, yeah. So now what I would like to do is now let's look at example 3. Example 3, let's look at it. Example 3. So example 3 is right here. Example 3. Okay, example 3. Evaluate 32 plus 35 plus 38 plus dot 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 and 101. Then we assume that this is an arithmetic series. Although that dot 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 is not well defined. So in this case, assume arithmetic series. Okay. Strictly speaking, I think on this example, I think did I right on the test? If I give you a series like this, then I will tell you that it's an arithmetic sequence. Strictly, this is dot 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 right here is not well defined. This dot 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 is not well defined. So if you want to argue from the logical science point of view, then can you tell what this dot 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 is? And the answer is no. Strictly, again, this dot 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 is not well defined here. So if I give you a problem like this, that will be a problem mathematically. So in this case, on example 3, I will have to tell you that this is an arithmetic series. That case, then this now will be fine. So I will have to tell you that this is an arithmetic series. So in this case, we'll assume that this is an arithmetic series, or I will give you some kind of condition, or I will tell you, assume arithmetic series, or the other way of saying that this is an arithmetic series is this. There's this right here. The argument of sigma is linear, but the general term is linear. General term is linear. If I tell you that the general term is linear, that means, what that means is that f of k right here, f of k is f k to the k, 3k plus 29, it is a linear function. This f of k is the general term. The general term is linear. And then basically I'm telling you that this is what? This is going to be an arithmetic series, the same thing. So most likely, what I'm going to tell you that the general term is linear. So that means f of k is equal to something k plus a number. It's a linear function. Then that becomes an arithmetic series. Now in this case, 32, 35, 30. So how do you get the sum here? This is what it is. First, find the general term. So now in this case, f of k is equal to 3k plus 21. It's not so hard. Why? 32 to 35, 35 to 38. How much does it increase as the order of the term goes up by 1? That is, from the first term to second term, it goes up by 3, and then from second term to third term, it goes up by 3. So what is the increment for each term? And that is 3. So that's why we have a 3 there. And then now, when this is the first term, we went k plus 1. With k plus 1, we need 32. So when you put in k plus 1, then we need a plus 29 here. So f of k is equal to this. And of course, every time you get the general term, always check. After you find the general term, always check. Always check. All right? Always check. In this case, if f of k is equal to 3k plus 29, plug in 7k plus 1. F of 1 is equal to 32. There we go. 32. First term, 32. Plug in k plus 2, you get 35 right there. 35. And then when k plus 3, plug in 3, k plus 3, then 3 times 3 is 9. 9 plus 29 is what? Is 38. There we go. So it checks out. So after you find the general term, always check. If the students find the general term, and then the general term doesn't work, and it's wrong. Okay? It's a very common problem. The students do something, and then it's wrong. Very, very common. So you have to check your work. Now, to find the order of the last term, let's see. So you want to know what order this 101 is. So what do you do? Let 3k plus 29 to the 101, and then you get k plus 24. That means the last term, k plus 24, what does that mean? That means the term 101. 101 is the 24th term. That's what I'm trying to say. So we have 24 terms in the series. The total number of terms is 24, or you can say that the last term is the 24th term. So that's what I mean by the order. The order means first or second or third. That's what I call the order. So the order of the 101 is 24. That's 101 is the 24th term. That's what I mean by the order. And then now, what is the sum? Sum is there for sigma 3k plus 29k equals 1 to 24. And now you can split the sigma here as a separate sum. That's part of the formula here. And then the constant multiple 3 can come out. And then this 29 can also come out too. This 29 you can either leave inside the argument, or you can bring it outside. Either way will be acceptable. Again, this 29 here, we usually leave it here, and then this sigma right here becomes 29 times 34. But to make it clean, I like to take out a 29, and then this guy actually becomes what? Becomes the formula number 0. So that's 24. So anyway, you get all that, and then you compute this, you get 1,596. So that is the answer to example 3. Any questions on number 3? Okay, now let's look at example 4. Example 4, we now have this right here. Example 4, we have this. 7 squared plus 8 squared all the way to 19 squared. Okay, so let's see. Solution 1. Why don't you first find the general term? Okay, general term? Okay. Now this one's easy because if you look at the expression, the number under the square, it's 7, 8, 9, 10. Looks like that's an arithmetic series, arithmetic sequence, where the increment is 1. So note that this guy is k plus 6 under the square. So f of k is equal to k plus 6 squared. Get this. Now check. When k plus 1, you get 7 squared. There you go. When k is equal to 2, we get 8 squared. We get 8 squared right there. K plus 3, we get 9 squared. We get 9 squared right there. And then, what is 19 squared? 19 squared when you get, we plug in when k equals 13. So I didn't bother to get that. We can just literally see it. So in this case, the last one is actually k equals 13. Not hard to see. K equals 13 becomes 19 squared right there. And so the sum is this. And then, when you evaluate this, you have to what? You have to evaluate this. And you split the sigma and then bring the constant out and apply all the formulas here. Apply all the basic formulas here, and then you can get the answer that way. Okay? So I didn't bother to get into the detail here, but you should be able to finish this up. Okay? Now, that was solution 1. Sometimes a problem has many solutions. Okay? It is very normal that a problem has many solutions. And I want you to kind of make observation and then search for other solutions. Now, let's take example solution 2. Now, in solution 2, let's see what happens. Solution 2, wait a minute, did I have, I thought I have solution, I guess it went to the next page, I think. What I'm going to do is let me save this page, and then clear this out. What I'm going to do is this, let me, how about this, I'm going to now clear this page. Let me now scroll this down. I thought it was like, oh yeah, you know what, I see, right, it went to the bottom. I went to the next page. Okay? So I guess, yeah. Okay, now let's look at example 4, solution 2. If you look at solution 2 right here, let's look at this. I want you to look at it. Example solution 2. Now, if you look at the sequence here, this is 7 squared, 8 squared, 9 squared, and then all the way to 19 squared. How about if you make the general term equal to k squared? Is that good? Well, in this case, if you plug k plus 1, there will be 1 square. Certainly, we don't get this series here. But what we can do is, if you let g of k be k squared, then what happens is, then the expression here, the expression in question becomes this sigma right here. We can have a sigma with argument k squared, but the problem is that the lower limit will be signed from 7. So this problem can be changed to sigma notation with k plus 7. So if the sigma starts from k plus 7, is that a good thing? What do you think? Can you apply any of the formulas there? Can you use those basic formulas? Can you use the basic formulas? Well, if you look at all the basic formulas, the lower limit is all 1. That's right. If you look at all the basic formulas, it starts from 1. It doesn't start from k plus 7. It starts from 1, not from 7. So, it looks like we're stuck. But, actually, we can do this. How about if we start up all the terms which are missing the front? So this can now be written as sigma k squared, k equals 1 through 19. So now you can use the formula minus the first 6 terms. Can you do this? Yes, you can. And then this will turn up your number, then minus another number. You use the basic sigma formula, and so we get number here, number there, and if you take the difference, then you can get the answer that way. So this is another method. Okay? So standard solution 1 is the standard method. Solution 2 is not so standard, but sometimes you do have an easier, simpler solution. Okay? So if you find the simpler solution, then that's good. Okay? So let me clear all this. Any questions here? Do you have any questions? Does any of you have any questions? No questions? Sounds good. Any questions?
No.
Did you know?
So the best answer is just to set up a equation correctly, correct? Not necessarily to actually solve it out.
You have to finalize this and finish it up and get the number at the end. If this will be a number. Evaluate this means you have to find the sum. Oh, by the way, you know, if I give you a problem like this on the test, I will make sure that the sum is long enough, because if I give you this very sum right here, like in example 4, how do you think students will add up all the numbers? What do you think students will do? If I give you this very problem, 7 squared plus 8 squared all the way to 19 squared, and then you have to add all these numbers. If I give you this very problem, what method do you think students will apply to actually get this sum? What do you think students will do?
They will actually go from 7 to 19 squared and then add them up.
And that's because in this case we only have 13 terms. So therefore, let me tell you this. On the example, this is what you see. That if I give you a problem like this on the test, then I'm not going to give you from 7 squared to 19 squared. I will give you 7 squared to at least about 7,000 squared. Is that clear? So the examples you see on the notes is short. So you can literally add them up. But on the test, I'm not going to give you these short problems. The short problems, that I will make sure at least there's at least 1,000 terms. Alright? That's my style. So don't be mistaken. Don't think that you can add them up literally, because on the test, that will not be possible. Alright? So don't apply that method. So I want you to apply, you have to always consider variations. So right here we have only 13 terms. So what happens if there's 1,300 terms? How about there's 2,000 terms? Now what? So I want you to prepare for that. So look for a solution which is general enough to cover those kind of problems. Okay? So if you just add them up, if you literally get to like 749, the 64 plus 81 plus 100, and the 19 plus 361, if you add them up all those numbers here, that's good. It will only solve this problem. That is solved because you have not developed a solution method. Your goal is to find a solution method which can be applied to other similar, longer, and more complicated problems. So I want you to do this in a more general way. So maybe when you practice, just cut off and maybe just do 3 problems right here and see whether you can work it out. So when you practice, don't make it long, just do this. 3 times 7 plus 5 times 10 plus 7 times 13. Can you find the sum here using the sigma notation? Of course, this is what 21 plus 50 plus 91. You can do it at the month. So when you practice, that's how you practice. That's how you practice your method. On the test, you're not going to find 13 terms or 3 terms. You'll at least find 1,000 terms. Okay? So be prepared. Be prepared. Your goal is to develop a method which can be applied generally. Alright? So do not trust, the shortness of this problem here. They are not easy, right? But if you add these numbers literally, that will waste of time. That will be completely useless. So don't do those numbers. Now let's look at example 5. This is what we have here. Example 5. Okay, so you got it. 3 times 7 plus 5 times 10, then all the 27 times 43. And here I put an argument here, the condition here. You put here the argument of sigma is quadratic. What that means is the general term is quadratic. So here what that means is the general term of the sequence, the general term. Write this down. What I mean is general term of the sequence now, not the series. You know what, you can say the general term of the series if you like. The general term of the sequence or the series is quadratic. Okay. So here we assume that the general term is quadratic. That is the general term. Let's say if I call this the general term f of j, I change the index variable to j to show you that the index variable can be any letter. So f of j in this case, well, what is that? What's the first thing is you have to figure out the pattern. What's the pattern? It's the 3 times 7 and a 5 times 10, 7 times 13. Now, if you look at the first factor of each term, the first factor of each term is 3, 5, 7. Oh, there's times here. The second factor is what? Is now, let me change my color. So 7 and 13. Oh, there you go. That's the pattern. So f of j is equal to g of j times h of j. So what is g of j? Oh, that's the sequence. 3, 5, 7, so on. That's j equals 1. There we go. So j equals 1, we get 3. So j equals 2, we get 5. So j equals 3, we get 7. There we go. That's it. What is h of j? H of j now is now the sequence. 7, 10, 13, and so on. The increment 3. So it looks like this is 3j plus 4. So now when you're plotting j equals 1, we get 7. When you're plotting 2, we get 10. It's 6. Okay. So the f of j is equal to 2j plus 1 times 3j plus 4. And now we want to know how many terms we have here. So now the last side here, why don't we look at the 27 term? Look at the 27. And that means that g of j, this guy must be 27. So when does that happen? Or j must be 13. So not hard to see. Or you can look at the 43 here. 43, and this guy must be 43. Or j must be 13. So either way, j must be 13. So in this case, the order of the last term is 13. That means the last term is the 13th term. And now we can set it up. Sum is equal to this guy right here. Summation notation is not ready, so this is not the summation notation. How you actually get the sum? Well, you have to expand it, and then split the sigma, and apply those formulas, and then you can get the sum. Any questions yet? Questions? If you have no questions, then here, you know what, there's nothing much here. I'm just going to clear this. I didn't say that screen, there's nothing written there. Now we get clear. Okay, any questions on this? Two questions. Back to section 4.1 notes, which has no solutions. Okay, no solutions, but I came back here because I would like to, I want to go through the problem. Now, remember, for every problem you do, you have to understand the problem. That's the first step. You must understand the problem. Okay? So, to help you, I came back to section 4.1 notes without the solution. Okay? So, already this guy actually has the solution already, but let's look at it. Okay, so any questions? Okay, now let me start. Now this area from here, this area is one example. I call it example A. It's actually the first example, and this example actually takes up the entire page. Five parts to it, but it is basically one problem. Okay? So the first step is this. Let's try to understand what this problem is and how about we are going to actually get to the answer. Okay, so first let's understand the question. So what is the question? The question is this. The question is, example A. Find the area bounded by y plus x squared and y plus 0 and x plus 1. Okay? So whenever I refer to some kind of area, this is the way I will describe it. So in this case, what is the area in question? The area in question is this. So let's say we have this x, y plane right here. So let me just draw this. And then now I'm just going to manually sketch this. Oops. Let me redraw this here. This is going to be what? This is going to be right here like this. Y plus let me draw this here. This is one. So let me draw a line here for a second. therefore I can draw the line like this. Then this point here is the point 1, comma 1. So if you write this one, this one is the point, comma, is the point 1, comma 1. It's a magnified one. And this curve, of course, is y of x squared. And this curve is y of x squared. Now the question is, we now want to find this area right here. This area. So what is this area? Can you estimate this area before we continue? What do you think? How much the area is about? Can you estimate? I'll take the whole square. That would be a 1 by 1 square. That would be 1. But this is far less than 1, and this is not even half. So can you all see that this area is going to be less than half? Yes or no? The area will be, in this case, yeah, you will soon figure out what the answer will be. But anyway, just by looking at the diagram here, because for all area questions, by the way, for all area questions, this is what I recommend. Before you actually find the area, I want you to make an estimate. An estimate, and then at the end, you are going to check your area against your estimate. Because if you find the area first, and then your area is a mistake, then you will not be able to guess anymore. Because you already have an answer, you're already biased. And so you will not have a fresh line, and so you cannot make an estimate yet. So I do recommend you to make an estimate before you actually get to the answer. Now this example will be a long solution, and therefore I am going to spend a lot of time here. But for the next example, I am not going to do all these steps here because there's actual theorem which shows that you don't have to do all of this, okay? So we'll just do part 1 and 2 instead of 5 parts. Okay, so the question is, how are you going to get the area of all this? What we want to do is this. First, we are going to find the area of this guy here in 5 steps. By finding the 5 steps, and these are the 5 steps right here, 5 things we will find. We will find f sub n bar. That's what I call n partial upper sum. First guy. And then number 2, f bar, which will be the upper sum. And then the third item we'll be finding is the f sub n underscore, which will be called the n partial lower sum. And then number 4, f underscore, will be the lower sum. And then number 5 will be the sum. Number 5 is a sum, and that will be, so then we call f equals sum. And this will actually be the area in question. So I should have said that this equal to A. So we will be at the last step, we will be finding the area. So we will find the area of this guy in 5 steps. And each step is quite long too. None of the steps are really that short. Especially number 1 and number 3 steps are quite long. Initially it will take more than 10 minutes. But once you get practice, it will not take that long, of course. So now what we want to do is, first of all, we have to know something about the area. The question is, what is area? How is area defined? So now we have to kind of go back and figure out how the area is defined. Most of the area is actually defined on a rectangle. So what is this? Area is defined. Area is defined on rectangle. So if you want area, if you want evaluate area, what do you need? Need rectangle. You might wonder, can you have triangle? Well, so why have a triangle? Don't we know the formula for the area of a triangle? Yeah, we know the area of a triangle. We know the formula for the area of a triangle. Don't we know the area of a circle too? Yeah, we do. But you know what? The triangle area, the formula, is actually based on a rectangle too. It's based on rectangle. How about the area of a circle? Is that based on rectangle too? Yes, it is. If you look at, the proof of the area of a circle, the radius r, then we get the area to pi r square. And if you look at the mathematician and Archimedes, he's an ancient mathematician of 2000 years ago, around 200 BC or something. He makes the first argument where the circle is chopped up into a rectangle. Is where the circle is chopped up and rearranged into a rectangle. So what I'm trying to say is, if you want to get area, we need to have what form? We need to have rectangle. Without any rectangle, no area. Without any rectangle, no area. Again, area of a triangle means, note that the area of a triangle form is half times base times height. Why do you think it's half of something? Why is area of a triangle equal to half times something? You know why? Because the half times base times height. The base times height is actually the area of a rectangle. So the area of a triangle is there, that equals to the area of a triangle is half times the area of a rectangle. Because you didn't know. So all the areas will actually based on rectangles. The two is you really rectangle. So the question is, this area over here is the only reason where it's going down. This is first. The question is, can you chop this up into finally many rectangles? Finally many than less than, you still need the same number of rectangles, and do that. When you chop them under rectangles, 1,000 rectangles, the middle rectangle is 10 to it. If you have curves around it. So, we will use infinite rectangles in order to get this area. That's why the limit comes in. If you have number 2, the limit comes in. We need to chop this up into what? How many rectangles? Infinite many rectangles. So now, here's the method which we'll go over now. To find the area, first step is to find the n bar, which is what I call the n partial lowest. This is the n partial lowest sum. Eventually, this s of n bar,
turn it down a little bit?
Lowest sum. Eventually, we will find, not this
Can you turn
bar,
it down a little
we
bit?
will find what we call the right sum. I'll talk about that too, okay? Okay, so how do you get the area of this guy? This is what we do. First, we have the interval from 0 to 1. We have the interval from 0 to 1. So first is this guy here. First, do partition 0 to 1 into n equal subintervals. This is what we call a regular partition. So what that means is chop this up. 0 to 1 into how many pieces? Into not 2 pieces, not into 2 equal intervals or 3 equal intervals, but into n equal subintervals. Now we have to use a primary. N is not 10 or 500 or 10 million, but n is fixed. But it will be it will be denoted as an unknown count, like a primary. So n is a fixed number, but we have to let this n go to then be a very large number. So therefore, we are going to chop this up into not 2 intervals or 3 intervals, not 100 intervals, but to n number of intervals. Eventually, we will let this n go to infinity. We will eventually let this go to n go to infinity. But right now, in part A, n is on infinity, n is just a number. An infinite is a natural number. Equals like a 2 or 500, but it can be any natural number. The chop this up in n in English, so what we'll do is we'll cut it up. 1, 2, and then dot. Then let's say we have an interval right here, and then dot. Now to do this here, what happens is this, I didn't write interval, did I? I should have said this. What I should have said is this. I sub k. What is the case interval? The case interval is equal to the case interval is equal to x sub k minus 1. X sub k minus 1 to x sub k. This will be our case interval. I don't understand what that means. So here we chop this up into what? Into k and n intervals. N intervals. So this will now be the first interval, I1. The second, this guy will be the second interval, I2. Now let's say in this dot, and this one, let's call this guy I sub k, case interval. And the last guy here, up here, the last interval right here, will be I sub n. So here we assume that n is actually a fixed number. So if you're not comfortable with n, then think n be like a million. we are chopping up into n number of intervals. If n equals 1,000,000, then that means we have million intervals, basically. Now let's just see what we have here. So now, and then the length of each interval. The length of each interval. What is the length of each interval? This length of each interval, we now call this guy delta x. Delta x is the length of each interval. So now, what is it here? The delta x is the length of each interval. This is delta x. If every interval is the same length, what is delta x? Delta x is actually equal to 1 over x. The length of the entire interval is 1, and we have chopped up into n intervals. So the length of each interval is now 1 over n. So the length of I1 is 1 over n, and the length of I2 is 1 over n. The length of each interval is delta n. That's the delta x. Now it is time to assign. So now the question is this point now, and let's name this now. This point right here, let's call this guy x0. And this point right here, let's call this guy x1. So we will name every point of the endpoints of every interval. So for the endpoints of every interval, now we have to name them. So this will be called x0 and x1, and this will now be called x2. And note that I1 is interval from x0 to x1. So when k equals 1 here, note that I1 is equal to x0, comma x1. So you can see this guy's that right there. So this is I, if I substitute k equals 1, then what is I for 1? I for 1 is equal to, substitute k equals 1, you get x of 0 to x of 1. That is the first interval. So then what is I2? I2 is interval from x1 to x2. And how about I to k? That will be, the left-hand point of I to k, that will be x of k minus 1. And then the right-hand point of I to k will be x of k. So now we have a pattern here. The right-hand point of I to 1 is x of 1. The right-hand point of I to 2 is I to 2. Second interval by x of 2. The right-hand point of the kth interval will be called x of k. And then finally the last interval, the left-hand point is x of k minus 1. It's x of n minus 1. And then the last guy will be, this one right here, will be x of n. So we now name all these points here. Now, let's figure out what's the coordinates of. So what are the coordinates of these x1, x's here? So x0, in our case, this is 0. What is x of 1? Note that x of 1 and x of 0 are delta x away. Therefore, x of 1 will actually be delta x. Coordinates will be actually 1 over x. So the x1, the coordinate of x of 1 will now be called 1 over x. And x of 2 is another delta x. So the distance from x of 2, x of 0 to x of 2 will be what? Will be 2 delta x. 2 delta x, so this is actually 2 delta x. What is 2 delta x? 2 delta x in this case is actually 2 over x. So that will be a coordinate. So these x's are coordinates. X's are coordinates. Everybody follow me here?
Yes.
And so, now if you look at x of k, this is x of k minus 1, what is that? That will be what? That will be k minus 1. That will be k minus 1 over n. What is our x of k? X of k is k over n. And then what is the last one right here? This is x of n. But x of n, you can plug it into this I sub k formula. If you now what is x of n? X of n is actually what? Is actually n over n, which comes out to be 1. In fact, x of n should be 1. So we get this right here. So now if you look at this guy, the formula is x of k is equal to k over n. So x of 0 is 0. X of 1 is 1 over n. X of 2 is 2 over n. X of 3 is 3 over n. And then x of 4 is what? Is 4 over n. And so on. So let's look at an easier case here. How about this? How about if you look at the case where n equals 3? Let's look at the case. When n equals, let's say, so for when n equals 3, how about this? Let's look at the interval here. So let's say, for example, let's look at the case when n equals 3. When n equals 3 here, how does the interval, how does the x look like? If n equals 3, that means this is 0, and this is 1. And we chop up into 3 equal intervals. We get this. Then what is the delta x here? The delta x will be, of course, 1/3. The delta x will be 1/3. The delta x is the length of each interval. So now we call this guy x0, and then this guy we call x1, and this one we call x2, this guy we call x3, and x3 should be 1 now. Now what is the coordinate now? This is the x-axis, of course. This is the x-axis. So what is x1? X1 is going to be, in this case, 1/3. And what is x2? X2 is 2/3. Just to remind you, delta x is the length of the interval, but x of I, or x of k, are what? These are what? They are coordinates. They are positions. They are coordinates. They are not length. They are coordinates. And of course, in this case, x2 is 2/3. That 2/3 happens to be the same as the length of the interval from 0 to x of 2. That's 2/3. So that's 2/3 here. Okay? So when n equals 3, if you do not understand anything, then let n be a number and see what's going on. So this is to help you understand the problem. Okay, so now what we want to do is this. Now the next step, we now have to get to the upper side. So what we want to do is, to get the area of this guy, what we want to do is, now let me change color. What we want to do is we chop it up here. In this case, we chop it up here. Then chop it over here. So now we see the area here. What we will do is we are now going to estimate this area from the upside. So we want to now create a rectangle which is just bigger than the area in question. So if you look at the first rectangle, if you look at the case rectangle, well, our goal is to find this area, but with this curve boundary here, we cannot get the area. So what we'll do is we'll estimate, we'll find the area of the taller rectangle, which is this. At this point here, now this point, why? Because this is the highest point. And so we are going to create a rectangle like this. We'll take that area. And then for the second interval, I2, we will add up this rectangle right here. And for the first rectangle, on the first interval, we will get the area of this guy right here. So we'll get area of this one, and then for the last side, we'll take the area of this tall guy, this guy. So when you look at this, you may say, oh yeah, it's not too big. But if you take the area of this guy, that will be the short rectangle. And this is what we'll do in part 3. But right now, we will get the tall rectangle. So when you get to part 3, the lower sum, when you get to the lower sum, we will add up all the lower rectangles, the short rectangle. So we will approach either side. So in this case, I'm going to erase the lower rectangles here. We are going to have a shorter rectangle. I'm going to just take the tall rectangle. So what we want to do is we want to find the area of all these little guys, and then we'll back them up. That's what we're going to do. So if you now this here, so what is this S of n bar? Let's figure what's going on. Now with S of n bar, this is the n partial upper sum, is equal to this right here. Sigma, first of all, we have n rectangles right here, n. And then each rectangle is called a sub k bar. So now this right here is called, this rectangle right here, the short rectangle here, the first, this rectangle here, I'm going to now call this guy a sub 1 bar. So once again, this, I'm going to call this guy a sub 1 bar. And then the second rectangle, we are going to call this guy a sub 2 bar. And in this guy, we will call this guy a sub what? We will call this guy a sub what? A sub, sorry. So this one, let me see, this, I want to wait this here. Yeah, so this is now called what? This is now called A sub 3 bar, A sub I bar, A sub K bar. This is now called A sub 3 bar, A sub K bar, not 3 bar, A sub K bar. This last guy, this guy is called A sub N bar. So it is the area of the rectangle. It is the area on that interval, but the area must be a rectangle. So we are now going to get the tall rectangle. And in order to get the tall rectangle, what we need to do is this. Now note that this is the case interval, and the case interval, we will get the height of this guy. Now this height is the function value at the right angle, which is I sub k. So what is the A sub k bar? A sub k bar happens to be f at x sub k times delta x. So if you look at this A sub k bar right here, what is the area of the rectangle? That is equal to f at x sub k, which is the height of this rectangle, x sub k. And then now, what is the base of this rectangle? The base of the rectangle is basically delta x. That is the area of this case rectangle, A sub k bar. Now, what is the area of this A2 bar? A2 bar is the rectangle. What is the area of that rectangle? That will be f at x2, f at x2. Note that x2 is the right exponent of the second interval, right? And then times delta x. You get this. So now what we get is, now you have to understand this. Now here, the hardest part of these kind of problems is you have to understand every detail. Every detail you have to understand. And I will be asking you to find the area this way. This is a point of definition of the definition of definite interval, or will be called by what we call the Riemann sum. Riemann sum. So anyway, you will see those terms again. Okay? So now here, what we see is this sigma right here is actually f at x sub k, and then times delta x. And then add up all these rectangles and take this 1 to n. And then if you add up all the, all those terms, then what? At the end, you would actually get the area. Get the area of the n partial of the sum. Okay, make sense? Now what I like to do is I'm going to save this picture. I'm going to save this picture here. And I know what? I wish I could keep this picture, but I don't know how to keep this picture. So I'm going to keep this picture here. So let me see. Let me save. And then let me just save it. So what I'll do is I will now go back. I'm going to go back here to the solution file, which has all the answers. So now let's go back to this here. This is how it's going to work. This is how it's going to be. Now, section 4.1. So we are at example 1, part A. So now let's look at part 1 here. We're trying to get the area. Now, from the second step, it's all mechanical, basically. It's all calculation. So now what we have is we have this right here. So we came up to here. And now from here to the rest of it, this is all algebra. There's no graph anymore. So what is f of x of k times delta x? Now delta x was the base of each rectangle. That is 1 over n. And what is f at x of k? X of k is k over n. So we get f of k over n. And then now, what is that? What is f of k of n? F of k of n. But what is that f? F is this guy right here. F of x is x squared. That's a function. So what is f of k of n? That would be k over n squared. So now we get this guy. Now we simplify this argument of the sigma. We now get k squared over n cubed. So we get this guy. Now from here to this guy here, now we can see this n cubed right here, we can factor this. Note that under the sigma, n is not a variable, k is a variable. K is a variable, n is not a variable. N is fixed here. So you have to know, sometimes n is a variable, sometimes k is a variable, they change. So every sigma is different. Here, under this sigma, n is a fixed number. N is a fixed number. Okay? N is a fixed number, k is the variable. So let me write this down. Okay, so anyway, n is a basic, n is a fixed number, and k is the variable. Now, we can factor the 1 over n cubed. And after we take out 1 over n cubed, then now comes the sigma k squared, k plus 1 to n. And what is that? Oh, now we can use the one of the basic sigma formula. This is the sigma k squared formula from 1 to n. So what is that guy? Now we get this. And what is this? Now we get this. And then we get this.
What? Yes, you okay?
So we now get the n partial upper sum. Any questions here? So what is this? What does this exactly mean? So now, in order for us to understand what's going on here, what would be a third partial upper sum? What is the third partial upper sum? Is f sub 3 bar. What is this one? The third partial upper sum would be 1 over 6, and at times plug in n equals 3, so that would be 4 over 3, and then what? And then what? And then if plug in n equals 3, then that will be 7 over 3. And then if we add them up, what do we get? We get this. So we can actually reduce this to 6 over 4. 6 over 4 over 6 can be reduced to 2 over 3. So that will be what? 4 over 3, 14 over 27. The third partial upper sum is 14 over 27. Now, do you think we can make sense out of this? So f sub 3 bar is 14 over 27. What does that exactly mean? Let's go back and look at let's see what we have here. So we have here the graph. The graph is y plus x squared, and the distance is 0. Now, how about if we chop this up into 3 intervals? So this is 1, then this is 1/3. This is 1/3. And this is now 1/3, and this is now 2/3. Now, we are trying to find the upper sum. So for only inches, so we are going to take this rectangle right here, and then take this rectangle right here, and then we take this rectangle right here. Can you tell me can you tell me the area of this small rectangle? Can you tell me the third rectangle here? We have only 3 rectangles here. What is the area here? What is the area of the first rectangle? Can somebody tell me the area of the first rectangle? What is the area of the first rectangle?
1 by 6.
1 by 6? What do you mean? This curve is y plus x squared. So what is height of the first rectangle?
1. Height is the 1. 1? Is it 1?
Area of the first
Oh,
rectangle.
the first one. Oh, that one. 1 by 9.
Is it? 1 over 9?
Yeah.
So 1 over 9 is the height. You're right. So now the base is 1/3. So what's the area of the first rectangle? 1 over?
9 times 27. Okay. I thought you meant the. Yeah, I thought you meant the third one. The third rectangle.
The tall rectangle, how much? The tall rectangle is what? 1 by 1/3? Is actually 1/3, so this is actually 1/3.
1. Oh, rectangle. Okay, sorry. That was.
Because the height of the rectangle, the tall rectangle is 1. And then the base is 1/3. So this guy's 1/3. Now what is the area of the middle rectangle, the second rectangle? What is the area of the second rectangle? Can somebody tell me? This is the case when n equals 3. When n equals 3, this is the third rectangle. Right? 3 and here's when n equals 3. So we have 3 rectangles. What is the area of the second rectangle? Now the right end point is 2/3, and therefore the height will be 4/9. And then the base is 1/3. So the secondary rectangle, the area will be 4 over 27. That is the area of the second rectangle. Now 1/3, while we have a common base here, this is actually 27, and then this is actually 9 over 27. So if we add up the first rectangle, and the second rectangle, and the third rectangle, what is that? If you add up the three rectangles, what do you get now? That's 1 over 27 plus 4 over 27 plus 9 over 27, and that will be 14 over 27, and we got the 14 over 27 right here. And the sum of all the three rectangles with partition 3 intervals right here, and that is what we call the third partial upper sum. Does everybody understand what the third partial upper sum means? Now, in order for you to be good at this, you need to know the algebra of all this, and you also need to know the graphical aspect. You have to understand the algebraic aspect, and you have to understand the graphical aspect. So you have so that you can see the connection between the two. So that's what n sub 3 bar means. The third partial upper sum. And that is the area of all the three rectangles when the interval is chopped into three parts, equal parts, and then we add up all the tall rectangles. So that's the meaning of the S sub 3 bar. There we go. Now, if you look at this guy here, you can see that the S bar, S of n bar, they're actually going down and down, get smaller. How is that? Because when n gets bigger, what happens? When n gets bigger, the n partial upper sum, they actually get smaller. So algebraically, that's good. But now, let's also look at this. Right now, in this diagram here, this is the third partial upper sum. Now, let's compare to the case when n equals 6. Let's compare to this guy. Let's compare to the case when n equals 6. I'm going to now put this in bold here so that we can see what's going on. When n equals 6, what we want to do is, n equals 6, then we get this. Now, the area under the blue, this is now the upper sum also. This is now the upper sum when what? When n equals 6. Now I can see what's going on. But now, when you compare the two, when you compare the upper sum when n equals 3 versus n equals 6, which one is bigger? The third partial upper sum or the sixth partial upper sum? Which is bigger? Can you tell me? Do you think f sub 3 bar, and that is f sub 6 bar, the sixth partial upper sum versus the third partial upper sum? Which one do you think is bigger? The third partial upper sum or the sixth partial upper sum?
The third partial upper sum is bigger.
Which one?
The third one.
Third partial upper sum is bigger or sixth partial upper sum is bigger?
The third one is bigger.
Which one?
The number 3.
This,
Yes.
so if you look at the third partial upper sum and the sixth partial upper sum, notice the last term here, we can see the best. If you look at the last interval over here, see the area in blue is obviously smaller than the area in red. Because the area in red is over here. This part right here is sticking out right here. And if you look at the middle two terms here, middle, 1/3 to 2/3, same thing. For the blue, this area is this guy right here. This is the area in blue. Area in blue is over here. Area in blue is over here. But the area in red is actually sticking out. We have this much more area right here. See, this much more area is sticking out. And therefore, you can see the red part is bigger. And so the red part included is the third partial upper sum, and the blue part is the sixth partial upper sum. We can clearly see that the third partial sum is actually bigger than the sixth partial upper sum. What I'm trying to say is, as n gets bigger, the upper sums are actually getting smaller. And you can see that graphically as well as algebraically. Again, you have to understand this algebraically by looking at the expression right here. And you should also be able to understand this graphically as well. So graphically, algebraically, either way you see, you can see that the n partial upper sums are actually getting smaller. Of course, when you draw the graph here, you cannot really compare f sub 3 bar and f sub 4 bar. That you cannot graphically, it's not there. Although algebraically you can see that. So for the graphical part, I compare f3 bar, the third partial upper sum, and the sixth partial upper sum. Again, cannot compare the third partial upper sum and fourth partial upper sum. That is hard to do, okay? You can actually get the area manually. You can figure out, but that's the algebraic way. But that's not the graphical way. All right, we'll do the fifth. So now what we see is that the f of n, the n partial upper sum, they're actually going down. They're going down, down, down. And so now we come to part 2. part 2 is now what? Is now called the upper sum. Upper sum, what is the definition of upper sum? The definition of upper sum is that we now take the n partial upper sum right here, and now we don't want to stop at 3 trying or 3 intervals or 10 intervals, 1,000 intervals. We now want to let this n go to infinity. So what happens as we chop more? Will this estimate of the n partial upper sum actually what? Approach a number? And it turns out, yes, it will approach a number, and actually will be a 1/3. So as number of intervals gets more and more, the area will actually will approach 1/3. So these guys here will really approach 1/3. This is approaching S of n, S bar, and S bar is actually approaching 1/3. So how do you know that? N is approaching infinity. Is anything being infinity? This guy's getting to 0, and that guy's getting to 0. And the whole thing will go to 1/3. So now what we see is that when you now compare our area to our upper sum, which one is bigger? Is upper sum bigger or is the area bigger? Compare our area under the curve versus the upper sum. Which one is bigger? Is upper sum bigger or is the area bigger? Can you tell me? Is the area bigger or is the upper sum bigger? Can you tell which one is bigger? This area is referring to the actual area under the curve. This is the area under the curve. This is the area under the curve. Area under the curve. And what is upper sum? Upper sum is basically the area of all the rectangles. It's not really the area under the curve. It's the area of all the rectangles put together. The sum of all the areas of the rectangles, and A is the actual area. So we compare the actual area under the curve versus the sum of all the rectangles. Which one is bigger? Upper sum or the area? Can you tell me? Can you tell me which one is bigger?
The upper sum.
Upper sum must be bigger. Why? Because upper sum always is sticking out. But the question is the difference could approach 0, so we're not sure. So when we take the limit as area approaching 0, who knows? They might be equal. So here the key point is that upper sum is bigger, but who knows? It might become equal. So here, I would like to stress the equal sign here. So we are not sure yet. It could be the same. Upper sum is either bigger or it could be the same. Because the difference here, the area which is sticking out, who knows? It might approach 0. So we are not sure. So that is now 1/3. So the conclusion at this point is that our area, we don't know exactly, but it is going to be either 1/3 or less. That's what we know. Up to part 2, that is the conclusion. And now let's look at number 3. Number 3 this time is now this. Number 3 this time is this. Now we have an interval here. We have an interval, and this is now x of k minus 1, x of k minus 1, and then up to x of k. Now this is the kth interval. Now remember on this interval right here, we have the curve right here like this. We have a curve. We have a curve like this. Right? And now, you know what? Let me draw this with a small red, thin red. And then now and then what we have is we want to create the area here on the K curve. Now on the first part on the upper sum, for the upper sum, what did we do? We actually took the tall rectangle. We took this guy right here. And then that's what we did. Now on part 3, we now want to approach from the lower side. So this time we're not going to add up the areas of all the tall rectangles, so we will add up all the short rectangles. So what are the short rectangles? The short rectangles are over here. The short rectangles, that means we are now going to cut out right here. And the area is therefore going to be now this rectangle right here. We will be now this one. You now want to find the area of this one. And now once again, this is the case. So this is the case. This is the what? This is the I sub k. This is the kth interval. And the area of this blue rectangle is now what we call a sub k on each interval. You know the tall rectangle. What is a tall rectangle? That tall rectangle used to be called h sub k what? H sub k? H sub k bar. The h sub k bar is the area of this guy right here. Here all the way, and then here all the way here, and then all the way here, and then all the way up to here. The tall rectangle all the way up to here. That was h sub k bar. That was there. But now we want to get the lower rectangle, the short rectangle, is h sub k underscore. So now let's look at number 3 here. If we look at number 3, this is what we see. And number 3 is x to that underscore. This is the n partial lower sum. Now it's kind of bottom of the screen. Can you see? But all of you see the screen here is bottom of the screen. It's not cut off, right? And now that is going to be the x of n bar is now the sigma. And once again, we have n rectangle. And now we add up all the h sub k underscore. What is h sub k underscore? These are all the areas of short rectangle right here. And then what is h sub k underscore? This h sub underscore right here, what is that? What is the area of this guy? The area of that guy is equal to this right here, is equal to the area of this guy. Let me change this to blue. The area of this guy is equal to, this guy right here is equal to, the base is delta x. And how about the height of the rectangle? That will be f at, not at x, not at the left hand point, but not at the right hand point, but at the left hand point. So we have now k minus 1. So we have this. So for example, if you have, let's say, what would be, for example, what would be like h sub k? What is h sub, how about that? So what would be h sub, let's say, h sub 3 underscore? What would be a third rectangle? What would be the area of the third rectangle? That is the third short rectangle. And that would be the function value of x2, function value of the f at x2, and it times delta. So I'm not going to do that here. But anyway, you kind of get the idea. That's that. And so what we do is now we get this. So this guy is actually equal to this right here. Okay, so what I'm going to now, I'm going to erase save, and then clear. Okay, let me just move on here. So we get this. Now we have part 3 underscore s sub n partial lower sum, and we get this. Now when you look at the third partial lower, the n partial lower sum and the n partial upper sum, number 1 and the 3 are similar, but the only tiny difference is we have this guy right here. X of k minus 1, and then that means we have this guy right here. This is x of k minus 1. And then that one is basically this right here. Instead of k, we have k minus 1, that's it. And then when you come to this sigma, we have this right here. And then we come to this guy right here. Now the question is, from here to the next step, now this is called reindexing. I'm going to explain this to you. Let me just finish the example. Okay, yeah, we have a few minutes left. So this part right here, what is this guy? This guy, when you multiply this out and you expand this, the red part only, this you know what, let me just pull out this here, this part right here. This part right here is this guy right here, which is, when you put k plus 1, you have to use 0 square. And then plus 1 square. And then what is the last guy? The last guy, and then 2 square. And what is the last guy here? The last guy is, plugging in, you actually get n minus 1 square. The very last guy is n minus 1 square. So we get this. So we get this here. And now, what is that? What I did was, you know what? Since the first term is 0 square, why don't I reindex this? So how do I write this? That one right there is now being the distance this way right there. That sigma right there is same as that sigma right there. Because they're both of these sigma, they actually refer to the same sum. It's actually from 0 square or 1 square all the way to n minus 1 square. This sigma right here has a 0 square, but 0 square is 0. This guy is 0, so we don't need this one. So the rest of it is the same. Same sum. And then now you apply the formula with a sigma k square formula of n minus 1 now, n minus 1, not n, then you get this. And then you get this. And then upper and the lower sums, you know what happens? The lower sums are actually going up and up and up. They actually go up. As you find chop more and more, the areas of lower sums, they actually increase. And so when you actually take the limit here, number 4, take the limit, the actual 1/3. Mistake here. The mistake is that, this one, I have a minus here. I think I need to correct this one. Anyway, the answer is 1/3. Let me make a correction here for 1 and number 4. B minus. Okay, I'm going to correct that here. I have a lot of mistakes, and this is not 1/3. So now, at the end of it, so we get that, and then at the end of number 4, we get this right here. So then let's see. We have A here, and we have the upper sum here, and we have the lower sum. Now, which one is bigger, our area or the lower sum? Of course, our area is bigger. Why? The lower sum is always the short rectangle, but it could be equal. The difference actually I have put 0, and so now what is this here? So we now see that the area must be bigger or equal to lower sum, but must be less or equal to upper sum. Upper sum is 1/3, the lower sum is 1/3. Now we're stuck, area must be 1/3. Okay, you know what? Let's take a 10-minute break. And right now the time is 9:55. So let's take a 10-minute break till 10:05. Okay? So we'll meet at, and we'll continue at 10:05. So again, 10-minute break. A 10-minute break until 10:05. Okay? So let me just save this. Then 10-minute break. 10-minute break. Continue at 10:05. Okay. All right, any questions? Okay, you know what? We'll be back in 10 minutes. Okay, do you have any short questions? Otherwise, we'll have a 10-minute break. We'll continue at 10:05. Okay. Does anybody have any quick questions before I take a break? Yeah, I'll be back in 10 minutes then. We'll meet at 10:05.